So the next topic under image enhancement is what is called contrast stretching. Contrast stretching. Okay, we all have some idea, right? When we say that we want to improve the contrast. Okay, but we would like to know, right, what exactly it means. Okay, in the image processing language. Now, contrast is again done to enhance visual appeal. Now, how much contrast should you increase or decrease in order to be able to? Normally, a contrast stretching means improving the contrast or increasing the contrast. So, in order to enhance the visual appeal. Now, how much should you do is again a subjective matter. Some people may feel that something is the contrast has been increased too much. Whereas some people might be happy with average contrast and so on. Okay, again, this is a subjective issue. Okay, which is why it comes under image enhancement. Now, there is a difference between contrast and dynamic range. These two are not the same. Okay, there is a difference between the two, and this can be explained by examining the histogram of an image. If you compute the histogram of an image, and suppose it turns out that it is very narrow. Okay, let us say what that means is if you have a max intensity I max and if you have a min intensity which is I min, okay, this is I max, that is I min, then you say a poor contrast, right? You will conclude that you have a poor contrast if I max minus I min is small. If I max minus I min is small. Okay, on the other hand, right, suppose you had an image that just had, let's say, right, two gray levels, something at 0 and something at 255. Okay, then we would say that such a thing has a high contrast. Okay, this would have a high contrast. Whereas as opposed to this has a low contrast. But then the dynamic range of this is higher. This has a higher dynamic range as compared to the one on the left. Okay, simply because dynamic range is the number of intensities that are actually non-zero in the image. Okay, so ideally, right, if you had an image that would occupy all these values, right? When suppose you had an image that would occupy everything down from right from 0 to 1 to 255, right? Then such an image would have a very high dynamic range as well as a high amount of contrast, right? Which would be probably the most ideal thing, right? Which you would like to have. But right, this would be something like a binary image. So a binary image, you would say, has a high contrast, but then in terms of dynamic range, it has a very, very limited dynamic range. This could have a reasonable dynamic range, but then right, this histogram indicates a poor contrast. Okay. Now in order to understand, okay, what these things translate to, okay, I'm going to show you an example. Okay, let's just look at the situation wherein let me see. Okay, so wherein when you see this image, you will understand, right, what we are trying to say. So if you see the first picture, right, this image is considered to have a contrast that is low, poor contrast. If you plot the histogram, right, you see that most of the values are in and around this range. Whereas so in that sense, the contrast is very limited. The dynamic range probably is not bad, but then right, when it has a contrast, that is really poor. And the whole idea behind contrast stretching, right, is to be able to take this image and apply some kind of a transformation on it, so as to be able to get an image that would probably look like this. Now, in this case, what has been done is what is called histogram equalization. The idea is that, strictly speaking, theoretically speaking, histogram equalization actually means that you take this input image and transform it in a manner that the histogram of the output, right, will occupy all the levels, right? It'll have all intensities in it, and all of them should occur equally. Now, in this case, we see that that may not be the case, but then definitely the histogram has now been stretched, so the contrast definitely has improved. Okay, at the output. Now, right, between actually a discrete approximation when we take this and then a continuous theoretical case, right, that there is going to be a difference, which I will explain down the line. But for the time being, just look at the image, and you would definitely appreciate that something like this is definitely better than actually seeing an image like that, right? So you have improved the contrast. Now, in the output histogram, whether the output histogram is flat, whether it occupies all the intensity levels or not, why that is not so, and all, right, we'll see later. This is all because of a discrete approximation. Now, following this, the histogram specification or histogram modification is not the same as histogram equalization. Now, in histogram modification, what we say is, suppose we take Lena image of Lena, and we know that this is an image that, let's say, every one of us appreciates, and then we all know that it has a good contrast, right? And then it has nice features, good contrast, and so on. Therefore, if you plot the histogram of Lena, it looks somewhat like that. Now, if you take the same landscape image that we had earlier, okay, which had a histogram like this, you could either equalize it, which is what I showed in the earlier slide, or you could say that change this image such that the new histogram would look like the histogram of Lena. Okay, so basically that is modification. So it need not be Lena. Sometimes, right, you might even have something else, but whatever image, right, you have a reference image, you have a reference histogram, which you think is good, and therefore, right, you want to modify your input image in a manner that after modification, the new transformed image, which is what is being shown here, would have a histogram that would mimic the histogram of Lena in this case, right? So this is called histogram modification. Now, both of these problems, right, are very tightly coupled, and therefore, we will try to propose a method which is a unified method that you could simply use it for either equalization or for the modification purpose. Okay. Now, now how we do this, right? I mean, how should we kind of, right, go about doing right this. Now, before we actually plunge into histogram equalization, let me just mention that. That there are also other ways. There are also other ways of doing into histogram stretching. What is called some simple techniques before you even plan to try before we even talk about how exactly should we do histogram equalization and histogram modification. There's something called linear contrast stretching. These are very simple methods, but then, right, they're not as effective as, let's say, histogram equalization or histogram modification. So in a linear contrast stretching, right, what do? We say that the input intensity should be mapped to an output intensity P out, such that P out is equal to P in minus C upon D minus C plus into B minus A plus A. Right? What do these things indicate? So P in, so out here, P in is the input gray level value. Is input gray level value. Now, A and B, right? A and B are the desired min and max values. That means after you histogram equalize, you would like A and B to be the min and the max values respectively. C and D, on the other hand, right, are the input the min and max values of the input min and max values of the image. Okay, that means whatever is the min and max value of the input image. If your P in is equal to C, then of course P out maps to A, which is the minimum value in the output image. If P in is equal to D, then D minus D and D minus C cancel off, and you get P out is equal to B, which is the max value in the output image. Okay, so one could do something like this, which is a simple method. Okay, it will give you some result, but then the most standard way, right, in which you want to do contrast enhancement is what's called histogram equalization. The other one is, of course, histogram modification. So we'll start with histogram equalization. Okay, equalization. Now, what exactly is this notion of histogram equalization? So what it says is that your input histogram could be whatever it is. So your input histogram could have whatever levels it has, and then could have whatever intensities it has. The output histogram. So given the input histogram, the output histogram should be flat, right? Should be flat. That means it should have all intensities in it, and then it should have all intensities occurring equally. Okay. Now, the whole idea behind this is, okay, it improves contrast. So, right, we can kind of, in a sense, right, say that it improves contrast by by better utilizing or better utilization of the available dynamic range. Utilization of the available dynamic range. I'll tell you what really I mean by this. Okay, this will become more clear. Okay, as we go on. Now, to start with, right, we'll take up a continuous case to understand how this works. Okay, to understand, so let's call this as HE, which is histogram equalization. To understand how HE works, histogram equalization works, let us first examine transformation of a continuous random variable. Examine transformation of a continuous random variable. Okay, and we will come from there, and then we will see, right, what will happen if you do a discrete approximation. We will take a continuous case, because in the continuous case is where we can establish the conditions under which this should be done. And then when you do a discrete approximation, you may not really end up with the same result that a continuous case, right, would have led to. But then, right, your discrete method, right, it is basically grounded on this one continuous theory. Okay. Well, now consider a continuous random variable. Let's say consider a continuous random variable. Let me write this as RB, a positive random variable, R greater than or equal to 0, because since we are dealing with intensities, right, we have this kind of a positivity condition with probability density function PDF given by FR of R. Okay, this is a reference PDF. Okay, this can be arbitrary in nature. Okay, this can be arbitrary in nature, right? We don't have any kind of a condition on this. Can be arbitrary in nature. Of course, it will satisfy all the conditions that a PDF is expected to satisfy. Otherwise, it can be arbitrary, right? And what are we seeking? Okay, let us say that has a cumulative CDF, right? That is a cumulative this one, a distribution function. Let's call it, right? Let's represent it as CDF, a capital FR of R. Okay, so where, right? So we know that FR of R simply means is equal to probability that R takes up a value less than or equal to R. Or this can also be obtained as integral 0 to R FR of W dW, right? So this equals the right area under your is FR of R. So if your FR of R integrates to 1, and suppose you want to find out what is capital FR of R, then you would kind of integrate the area under this PDF, which is FR of R, and and then you would find out what is FR of R. Now, what is the goal? The goal is to apply a transformation. The goal is to apply transformation, or is to apply. Goal is to apply a transformation such that or let's say goal is to transform the random variable. So transform the random variable such that the new random variable, such that the transformed random variable, let's say S, has FR of S, has a PDF, let's call it FS of S, is equal to 1 in the interval 0 less than S less than 1 and 0 outside. Okay, so which basically means that you would like this to be uniformly distributed. Right. So in a sense, what you would like it to be is to go like 0 to 1, and 1. Okay, this is what you ideally would like your fs of s to be, and 0 outside. Okay, now what should be that particular transformation, right, which we need to apply in order for this to happen? So you can think of s to be equal to some t of r, and what should be t of r? What should be t of r, right? So that what should be t of r? So that fs of s is 1, right, in the interval 0 to 1, and it is 0 outside. Now it turns out that the t of r is in fact equal to fr of r, okay, which is the CDF of r. Okay, this is also called probability. Okay, such a transformation, this is a standard thing. Such a transformation is also called, such a transformation is referred to as a probability integral transform. Probability integral transform. Probability integral transform. Okay, so such a transformation is referred to as probability integral transform. So then what this means is that s equal to fr of r. Okay, and then in general, right, if you had s equal to t of r, then we would have said fs of s is equal to fr of t inverse of s. Okay, we are looking at a scalar random variable divided by ds by dr modulus evaluated at r equal to t inverse of s. Right. Now, given that s equal to fr of r, right? So ds by dr is simply fr of r, right? And therefore, this term becomes mod of fr of r. However, but fr of r is always greater than or equal to 0. Therefore, this mod has no implications here in this case. Therefore, what you will get is fr of r evaluated at r equal to t inverse of s. Right? Now, provided you choose s equal to fr of r. Provided, of course, right, you choose s equal to fr of r. Okay? Provided you choose this, otherwise not. Okay? Therefore, which is okay. So when you do this, then what you get is fr of t inverse of s, and then you again get fr of t inverse of s, or in this case, it's basically fr inverse of s, and therefore, right, this is equal to 1. And because of the fact that s is fr of r, and fr of r will always have values between 0 and 1, right? So fr could be something that grows 0 all the way to 1. Okay, this will be your fr of r. Okay, if you plot it versus r, and therefore, right, what this clearly shows is that you have an fs of s that is equal to 1, and then s takes values in the range 0 to 1. Okay, which is what you wanted. So this probability integral transform is what you need to apply, right, in order to be able to equalize the histogram, or in order to be able to arrive at a final kind of a PDF that is going to be flat, uniform. Now this would be right, a theoretical result. This would be a theoretical result. Well, if you want it to be even more clear, then you can in fact write this as fr of fr inverse of s divided by fr of fr inverse of s, okay, which is equal to 1. Because t inverse in this case, when you choose the special case of s equal to fr of r, this is what you will end up. Now, right now in reality, right? So in reality, of course, whether you get a flat histogram or not, when you have a discrete image, right, at a discrete set of intensity values, what will happen is something, right, that we would like to wait and see. Now, instead of histogram equalization, suppose what you wanted was histogram modification, right? That is just a small step away. So histogram modification, you can again write along the same lines, okay? And we can in fact have a unified kind of, right, a method which we could use for both histogram equalization as well as histogram modification. Now, modification, what does this entail? It says let fr of r and fz of z, be the input and output be the input and output be the input and output PDFs. That means fz of z is simply a desired PDF, whereas this fr of r is your input PDF. So you want to again transform it. You want to transform random variable r to random variable z such that z has a PDF fz of z. Now, in order to do this transformation, what we'll do is the following. Let us first transform r through PIT. Let us first transform r, that is the input random variable, through PIT, which is simply a probability integral transform. Let's say that right, we get so suppose we do S equal to fr of r. So we know that S is uniform and so on, right? That we have already shown. Let us also transform Z, okay, using PIT, which then means that let's say that we get some other variable. Let's say v. This is not r. Okay, this is v, and let's say v is fz of z. Okay, so now v is also uniform, right? Since you've applied a PIT on z. Okay, so you get v is also uniform, s is also uniform. So what this means is that now if I want to know what transformation should I apply in order to get z, so z is equal to fz inverse of v. But then since both v as well as s are uniform, right? Instead of putting v, I might as well put fr of r, right? I might as well put s, which is fr of r. Okay, so it means that if I start with an input random variable r, I should do fr of r, the CDF, and then I say perform fz inverse on that in order to be able to get this transformation, right? So if you want to do a modification, this would be the rule, right, that you would have to apply. Now, in case it so happens, now why I said that both histogram equalization and histogram modification could be done under the same roof is because if, let us say, if it turns out if z is already uniform, okay, if z is already uniform, okay, in the sense that that means to start with, this is already uniform, then we know that fz and fz inverse are both the identity, are both identity functions, and therefore, okay, and therefore your z, right, which should be your transform variable, should be simply fr of r, which is what we said we have to do if you wanted to do histogram equalization, right? So that means when so the point is if your final z is actually uniform, right? If it is already right, if you're not asking for something else and if you're simply asking for a uniform random variable, then they say transformation, right, which you seek in order to kind of get a z that will be uniform, will then be fr of r. Okay. So yeah, right. This is easy to show because right, if you see the CDF of a uniform random variable, right, then it will go like that, and then it will hit 1, right, and therefore you've got like 0 to 1, okay, and then this will be 0 to 1, and therefore right, anywhere you pick a value, let's say z naught, okay, then right, that'll take a value z naught here, and therefore, right, fz of so if you look at it as, okay, this is fz of z, then versus z, then fz of z naught is z naught, and fz inverse of z naught is also z naught, right, and therefore, okay, this is an identity mapping, okay, which is why z will then be, so the transformation that you need to apply so as to transform r into a uniform random variable will be simply fr of r. Okay, this is what a continuous theory says. But then in reality, right, what we have is actually a discrete grid. Right? We have only a histogram which exists only at certain right? Only so we have a discrete set of intensities, and therefore, right, a discrete approximation is what will happen. Now, because of that, right, certain things will not happen the way you would ideally like them to happen, but still the implementation, right, when you have a histogram implementation that follows this law, but then at the same time, right, you have to make certain approximations in order to be able to arrive at the final result. Okay, I'll take an example in order to explain this. Okay, this is best explained